Today we are going to start looking into these sentences in the Sola algorithm, which is about stability. We have to find a delta t, which is as big as possible without the code actually exploding. We want to have a good solution quite accurately, but we don't want to spend days or months simulating, so we need to find a good delta t. So that's our aim here. When we are talking about stability, you have several methods that you may use to find a criteria for the time step so that your simulation doesn't explode. But here I'm going to teach you a crude method. It's simple, and sometimes it even works. It's not precise, it's not correct, but it's very easy. And in this course that should be enough. At least you will have an idea what's going on. The other methods for Neumann, stability analysis, matrix methods, you'll find in other numerical courses. So how do we deal with such a complex equation as the Navier-Stokes? So here I am just picking some terms from the equation. Some terms from the Navier-Stokes. And when we do the stability analysis, we don't really do the entire equation. We don't do everything. It's too complex, rather messy equation. So we split it up and look at only certain terms at a time. So the first terms we are going to look at is they are these two. And then we are talking about advection equation. That's where we start. Next, we are going to look into the time derivative and then the last term. Then we are talking diffusion equation. And finally, we will also look at the advective acceleration terms and the diffusion term as well. So it's a mix advection diffusion equation. Advection diffusion. And from these three say model equations, hopefully then we will learn something about how big time step we can use. If you look at the last choice, only the acceleration term here, advection acceleration, and the diffusion term, I have skipped the time altogether, so delta t shouldn't enter into the problem. Still, he will give us some requirements. Not necessarily for the time step directly, but he will give us a requirement for the delta x, how small your delta x has to be. So this is the plan. So we start with the advection equation. Only the two first terms, and I cheat because here you have a nonlinear term. function multiplied with the derivative of a function. I don't like that. You can't really do any analysis with a non-linear term, so we cheat, we linearize. This velocity here in front of the derivative, we call him something else. So we write du dt plus a, and then du dx equal to 0. So this is a linearized version of the advection equation. Okay, we want to take this equation and we want to crunch it numerically. We have to make a discretization of it. And I choose the simplest, forward time, central space. Forward time, central space, numerical schemes. Popular, you call it FTCS schemes. They are widely popular. Typically the first one you will try, it's very easy. Forward in time, meaning a first order Euler scheme. Central in space, meaning second order accurate discretization schemes. So very, very easy indeed. Let's see, we have, what did I use here? J and N. So for the time derivative, the discrete positions will now be J, so it's a one-dimensional problem. You only need one space index, but the time is a superscript, so the new time level will be n plus 1. And then create a time derivative, so this will be minus the old one, divided by delta t. Plus, and then the constant velocity a. And now I need a space derivative. But it should be central. Central around my center point j. So here I have to use u j plus 1 minus j minus 1 divided by 2 times delta x equal to 0. And what time level should we use here? Well, remember, first order forward time, Euler scheme. Everything else should be old values. So here, time level n and time level n. So this will now be the recipe. It's first order accurate in time, second order accurate in space. Everybody with me so far? Should be straightforward. Now we write this one a little bit. We write it on the form u j n plus 1 equal. I mean, this is an explicit formula, so if you know everything at time level n, it's very easy to find what's going on, what's going to happen at time level n plus 1. So what do we get? Well, this guy goes on the other side, j n, and then these two guys over the other side, they will change sign. So this will be now negative. We will have delta t multiplied with a over 2 times delta x, and then these two guys inside here. And minus uj minus 1. There we have it. Now delta t multiplied with a divided by delta x, that one is quite famous. So delta t multiplied with a over delta x, we call it c. This is the Courant number. So what's the dimension? Well, you have time multiplied with a velocity. That's going to be a distance, then divided by delta x. This is non-dimensional. So then we can find our Courant number here, like that. And we can write our equation like this. Uj n plus 1 equals Ujn minus 1/2 Courant number multiplied with J plus 1 and Uj minus 1. So this is my recipe, this is my numerical stencil, and this one shouldn't be any problem, should it? Now the question is, how big time step can we use here and still get a solution? That is the question. Well, this advection equation, it is just the first order partial differential equation. So when we talked about classification, elliptic, parabolic, hyperbolic, it really doesn't fit the description. But it has hyperbolic nature actually. So it is hyperbolic. But it only has one characteristics with characteristics dx dt equals this velocity a. So physically what this equation does, he will take a signal u and then move this signal with the constant velocity a0 or a. So that's physically what he does. And if we want a solution now, forward in time, and here we have x, then here I have my point J. So this is my center point here, time level n. And now I want to go up to time level n plus 1. How do I do that? Well, I use the center point, of course, but also I use the two neighbors. So here, J minus 1, and here, J plus 1. I use those three to construct the new one up here. So this is my discretization star, normally what we call it, when you draw it graphically into space, in this time-space diagram. So if you now look at this Courant number, what will it represent? Well, delta t times a is distance. This means that the signal is moving at a certain distance during one single time step. How far will you be allowed to move during one single time step? Well, look at the stencil here. I have only used the closest neighbors. I don't use j minus 2 or j plus 2. They are not involved in my discretization scheme. Meaning this information here, when it travels during one time step, should not travel longer than one single delta x. So this distance should be smaller or equal delta x. This also compares with this hyperbolic boundary conditions we talked about, because when you know information in a given range in your x-axis. You only have this information. Where can you find a solution? Well, that depends on these characteristics. And then, I should use another color here. Pink. If these are the characteristics, they could go either positive or negative way. So this information at this point is traveling to the right or to the left, depending on the sign of the transport velocity A. Same goes with this point, could go back or forward. And then we talked about this sector here. That was the influence sector. You change any value inside this range, you will change the solution inside this sector. So that was only the influence. But the solution area, what was that? That was inside this triangle. So that means you must choose a time step, a delta t, smaller than this one. So that is actually what I have said here. So what we call a Courant condition, delta t multiplied with a over delta x must be smaller or equal 1. This is quite famous results. It's called a CFL condition. And CFL stands for Courant. The F, that is Friedrich. And L is Levy. Courant-Friedrich-Levy condition. So here we have taken it, say, from the hyperbolic nature of the equation. But also, you can sort of think for yourself here, yes, it makes sense. You shouldn't let information travel longer than one single delta x during one single time step. If we had involved more neighbors here in the discretization, yes, we could have done it, but we haven't, so now we have to limit ourselves here. Yes?
If the delta x differs from j minus 1 to j and j to j plus 1, is the smallest, or?
Yes, so that's a good point. If delta x is not a constant, and in more complex codes, it won't be. You can have very small delta x's somewhere, and then you can have very big delta x's somewhere else. You have to check this condition for every single cell inside your computational domain at every time step. This can be tricky. Imagine you have the following problem. Here you send in a velocity u equals 1 meters per second. Then you push this into a channel, and all of a sudden you have narrowed the channel down a little bit here. And then you have an outlet out here. Simulate this one. Of course, we have to make a mesh, discretize our domain. So here we can use quite large meshes, and also here. But in this region here, a lot of things is going to happen. You will have a quite speed up of the flow. It's a very narrow opening, so the velocity here is going to be big and sharp gradients. So we are going to use a lot of cells in this tiny little region here. Okay, now what's going to happen here? In this region, delta x is going to be very small. And the velocity is going to be very big. Remember, it's not a constant velocity, really. It should be the same as the unknown velocity. So he's going to be big, meaning to get this ratio smaller than 1, you're going to have to use a very, very small time step. But you should check this at every cell during your simulation, yes.
And delta y?
Delta y goes exactly the same, yes. Nevertheless, if if you look at the Solar code, delta T should be smaller than H, he says here. Delta T should be smaller than H. So what happens to the velocity? Well, in this code, now you don't see anything. How come? Ah, I had some double screen. Thank you very much. This one I haven't tried before. Delta T should be smaller than the smallest of, and then we have three separate criteria. The first one is just delta T smaller than H. And H, that's the same as delta X and delta Y. So the first criteria here, just delta T, yeah, it has to be smaller than H. If not, you will get a warning. You will still be allowed to simulate, to run it, but it won't work normally. That's the stupidest double screens I ever seen. I have to have it here, thank you. USB. Ah, no, not that one. That's the editor. So here is a small little demo program. Let's try to run it and see what happens. Change folder. There we go. So here I have a region in space. And I have initially a signal that is 0, except here is 3. So the blue one, that is my unknowns U. And then I have a constant velocity. And I have now chosen a time step so small that the CFL condition now should be 0.1. Which is well below the criteria here. So this should be very safe indeed. Doesn't look good. Because the correct solution here should have been my initial signal, this square, should just move undisturbed. Instead we get all this noise. So something is fishy here. And now if we try with a smaller time step, and then again. Now the CFL is 0.01. It actually doesn't help. So something is wrong here. It's unstable. But I haven't violated the criteria, so it should be stable. What's going on here? What is going on? We check the stability criteria for this one with a method So a very simple method. I don't have a real name for it. I call it max-mean method. Others call it positive coefficients methods. But the method, although not a good name for it, is still widely used. So let us quickly go through it. Let some unknown x, or u if you like, these are our unknowns, be written in the form coefficient multiplied with one value, and then another coefficient, another value, and so on. And here all these a's I assume are positive. That is first assumption. First assumption. I assume all of them to be positive. Normally they will be, but not always. Next, we define a minimum of these x's. X-mean, that is the smallest one of all my x's here. x1, x2, and so on. Also, we define x max, same way as the biggest one of all these x1, x2, and so on. Of course, this x1 and x2 and x3, they are whatever you find on the other side here in your discretization stencil. If you define it like this, then when we sort of create our new value here based on the right hand side, we can write the following. I can write it here. The x mean multiplied with, and now the sum of all these coefficients must be smaller or bigger, smaller or equal to this new x, which again must be smaller or equal x max, and then multiplied with the same sum. Like that. And then we have another if sentence. If now the sum of all these coefficients equal to 1, and that happens frequently actually. So if a1 plus a2 plus all the coefficients equal 1, then we can write the following. X mean smaller or equal x, smaller or equal x max, which means x is bounded. He will be in between the maximum and the minimum value. He will never explode. It is stable. Then we have a stable scheme. So that's actually the theory behind this max-mean method or positive coefficient method. Very simple. And it's very crude. So if it works, you will find a criteria which, well, you are dead certain that this will be stable, but it's not the precise criteria. It's not the correct one. It's not what we call the necessary criteria. It's only a sufficient criteria. But let's try to use the method. That's the theory. Any questions to that one? It's okay. So let's try it. We had two ifs. This was 1. The sum of the coefficient has to be 1. And another if, all the coefficients has to be positive. That's the second one. So we have two ifs to be able to use this method. So let's try it here. Here we have the stencil. Then I sum all the coefficients. What is the coefficients here? Well, we have one coefficient in front of uj. He is 1. Then I have a coefficient in front of j plus 1 here. That will be minus 1 c half. And this one shouldn't be plus, it should be minus. And the coefficient in front of him will minus minus, so he will be plus. So that's 1/2 c. And there you see, when you add all the coefficients together, you will get 1. Okay, we can use the method. The sum of the coefficients is 1. So the next demand, all the coefficients, all coef should be positive. You write an A upside down, meaning for all. So all the coefficients should be positive. Well, the Courant number, the C itself, is of course a positive number. We have a positive delta T. A, I have chosen positive, and delta X is of course positive, so the C is positive. Meaning the first coefficient, no problem, and the last one, no problem, but the one in the middle, that's impossible. So here we just have to say all the coefficients positive, no. Meaning this is unconditionally unstable. So it doesn't work. It will never work, according to this. Doesn't matter what you do, you will have a big trouble. It will always explode. People have tried playing around with this equation in many ways, but the problem actually remains. You can't really get out of it. So it's a big problem. How can we remedy this one? We have one trick that you should be aware of. Using smaller and smaller time step didn't work. Now I use a big time step. Now I have chosen my delta t to be 1. A is 1, delta x is 1. So now I have a Courant number of 1. That is sort of you pushing the limit here. The c should be smaller or equal to 1. So now I'm just on the limit. But now see what happens. Well, that didn't really work well, did it? What's the problem now? It should have worked. FL is 1A. What was it? A0. Thank you. A0 should be 1, and delta t is also 1. That was strange. No, sorry, my mistake. Now it's quite okay. It really doesn't help. He will explode no matter what. So we have to think differently here to be able to find a solution. this recipe here, that was from the forward time central space. One remedy is to use not central in space anymore. So now we are talking a first order upwind scheme. So we had the equation, time derivative plus a du dx equal to 0. And now we do the following. It's still first order forward in time. So here we have the same term, uj n plus 1 minus uj n over delta t plus a. But now it's a question with this velocity a. Is it positive or negative? Here I choose this one to be positive, meaning the information will travel to the right. So when we had this figure here, x and t, here was point j, here was point j minus 1, and here was point j plus 1. Time level n, and up here time level n plus 1. So I want to have the new velocity here. But when I now create this spatial derivative, I do it with the sort of an upwind philosophy. The information is traveling in this direction with the velocity a. So when I now create a derivative, I don't use a central scheme. I don't use these two. I take the one upwind, upstream. I use these two only. So now my discretization star will look something like this. So here, this derivative will now be uj n minus uj minus 1 over one single delta x. And now this one equals to 0. That is the first order upwind scheme. And the philosophy is then based on the information is traveling here with the velocity a. So finding a proper new value up here will then mean you sort of look in the direction that the information is moving. So that's the philosophy behind it. The price we have to pay, this is now not equal to 0. It is equal to 0 plus order delta t and delta x. So the accuracy in space has gone down by one order. This is a first order in space also. So what will my recipe be now? uj n plus 1 equal, what will we get? You will have uj n here, but you have one here as well. Now let's see. So he will have the coefficient 1 from him, and this one on the other side will be negative. That will be delta t multiplied with a over delta x. That is my Courant number. So that was uj. And then I have uj minus 1, negative, but on the other side he will be positive. And the coefficient in front of him will be just the Courant number, uj minus 1. So there you have the upwind scheme. And is it stable or what? Let's check. The sum of all coefficients now equals Well, for the uj, you have the coefficient 1 minus c. For uj minus 1, you have the coefficient plus c. And yes, the sum is 1. Okay, we can use the method. Next, all coefficients must be positive or equal to 0. But for this coefficient, that's not a problem. But here you see 1 minus c has to be positive. So the demand will be 1 minus c should be positive. In other words, you get the Courant-Friedrich-Levy condition back. C must be smaller or equal to 1. So now we are back with the CFL condition. Now let's see if this one works. First order upwind, and we can start with a delta T, say to be a small one. CFL is now 1 over 100, and now I have this method. And yes, it is stable. But we pay a price. The correct solution should be the red box, should be square. So you see we have smeared out these sharp gradients on each side. And if we increase the time step by a factor of 10 and run again, you get the same effect. So yes, it is stable, but rather inaccurate. So that is the effect with the first order upward scheme. Any questions? Then we take a break. Okay, we start up again. We have found a solution for our advection equation by throwing away the central space scheme and using now a first order upwind. Yes, you get a stable solution, but a nasty price. Now we can just to show change for the first order upwind scheme. I have now pushed the time step all the way to the maximum. So now my CFL number equals 1. And finally, yes, you get the correct solution. So now what happened? Well, if you remember the stencil that we had, the first order upwind, when was it? It was something like this. N multiplied with C, wasn't it? Yes. And if you now choose, as you can see, choose a C equal to 1, this one disappears. And you are left with uj here, number j, n plus 1. The new velocity here is directly this one. So the only thing that happens is you take the value you have here and you transfer it straight up here. And choosing the time step so that C equals 1, that is actually to adjust the characteristic curve so that you hit this point exactly. So now this one has the correct slope, So you have delta t over delta x, so that the velocity a equals delta x over delta t. So what we have done now is actually used hyperbolic solution techniques. You rewrite your partial differential equation in a direction along the characteristic curves. Then the partial differential will be reduced to an ordinary differential equation. So yes, it's possible here to find a solution, but that is then with hyperbolic techniques, so it really doesn't help us. Also remember, the advection equation is only part of the entire Navier-Stokes, so this is interesting, but not really helpful. You have other techniques people have been trying here, some hybrid schemes. Let's see, number 4, where you take 50% of the upwind scheme plus 50% of the central scheme, and it really doesn't help. You have you have fully implicit schemes as well. We'll come back to that, but no matter what you do, it's unstable and the solution will never get nice. So for now we just keep it as a nasty problem. So it sort of looks like we should give up with the central space scheme, but no, because you remember the Navier-Stokes. First of all, it looks something like this. It's not linear, it's a non-linear term. And then you have something else here on the other side. Pressure minus 1 over rho. You have viscosity, double derivative, and so on. So you will have real viscosity into the problem. This effect here, that we have taken a sharp gradient and now sort of smeared it out, soften it, that actually means we have introduced viscosity into the equation, and it shouldn't be there when you only look at the advection equation. So it's a very bad solution either way. But for a big problem, a real problem, we will have viscosity anyway, so we will survive, we'll find a solution. So that was the advection equation. Any questions to that one? It's okay. Next, diffusion equation. The derivative equals viscosity double derivative with respect to x. So we are doing the same here, and we start out directly with a forward time central space scheme. Then we should have more or less the same recipe as for the advection equation, at least for the time derivative. Like this. And then on the other side, what do we get? Viscosity, and then a double derivative. What's a double derivative? Central space. Well, you use j plus 1 minus 2 times the center point plus j minus 1. n divided by delta x squared. And we rewrite this one on the form the new velocity equals, this is also an explicit formula. This equation here, it's not hyperbolic, it's parabolic. So it's fairly easy to find a recipe here. You can march your solution forward in time by saying the new one equals just old values. So what do we get on the other side? you will have UJN, and then from this guy, but we have something here as well, so it will be then minus 1 minus 2 times of, and then we will get delta T, viscosity over delta X. I call that one small r. And I get the same for these two guys as well. So that will be r multiplied with uj plus 1 and uj minus 1, comma, r equal to delta T, viscosity over delta X squared. So here is my recipe. So what does the stencil look like? Well, we are using J minus 1 and J plus 1 to construct the new one. So this is the discretization star in space-time diagram, identical to the one that we had with the advection equation, the first version, the central space scheme. What about this one? Is it stable? Well, let's have a go with this stability method. Sum of the coefficients equals, I have a coefficient in front of uj, that is 1 minus 2r. Then I have a coefficient for j plus 1, that is an r, and the same for j minus 1, another r. Equal 1? Yes, you may use the method. So the sum of the coefficients very, very frequently becomes 1. So it's a very neat stability analysis, very easy method. And now the criteria: all coefficients must be positive or equal to 0. Well, the r itself is of course a positive quantity. Positive delta T, positive viscosity, delta X squared is positive. So these r, they are not a problem. It's this parenthesis that has to be positive. So if everything is going to be positive, my r must be smaller or equal than 1/2. This will be the demand for stability. So let's check it out if that one is correct. So here we should have something, FTCS, yes. We'll just try and see what happens. Oh yeah. Diffusion. Interesting. I can't call them diffusion. It's words that MATLAB has been using. Okay. Call them something else. Diff. Thank you. Here is a physical problem. And it is actually the startup of a cuvette flow. Because if you look at the equation here, no pressure gradient, no gravity, no convective acceleration terms. These advection terms, they are disappeared. So this is what you are left with in a correct problem. So what should the solution be? You start with everything equal to 0, and the correct solution should then be a straight line here. And I have chosen my delta t so that we are just on the limit, r equals 1/2. Oops. And here it runs quite nicely. And the arrow S is not that big, so yes, we can believe this one. It's stable, and it tends towards the correct steady state solution, just a straight line, so that's quite okay. So now let's try to increase delta t a little bit. It's still running. Just crashing. A little bit bigger. So now it says 0.525. It's not smaller than 0.5. So this is a little bit above the stability criteria. And yes, it explodes. And it's actually quite amazing how touchy he is. I mean, you can even try with a 0 here. I think he still will explode. Getting more and more shaky, and yes, rather strange actually. One might imagine that he should explode in the beginning. I mean, you have this solid wall moving all of a sudden, and then the lower wall is steady. So the first time step, what's going to happen? Well, you will have 0 velocity here, and all of a sudden a very big velocity up here. So one should imagine here it's a sort of a problem area. Here he should explode. But no, he doesn't. He can get almost all the way up here, and then he starts shaking it in the middle. I don't know why. So the point is here, he will follow this demand very closely. So that's definitely something that we have to take into account. And also, if you look in the Sola code, we will actually have this limitation. I think it is the last one. This r should be smaller than 1/2. R was given here. Let's see. This should then imply delta t must be smaller than, what will it be? 1/2. You will have delta x squared over 2 times viscosity. So actually it will be this amount. It will be a little bit different in 2 dimensions. So yes, this one is also listed. And physically, what does it mean actually, this criteria? Well, it's something to do with the total amount of diffusion into your problem. And the diffusion, this term, you will actually have, due to this scheme, some additional terms here in front of this double derivative, which will be negative. And a negative diffusion, that is dangerously. What does a diffusion mechanism do? Well, if you have a sharp gradient, a jump in a quantity, he will tend to smear it out. That's positive diffusion. Negative diffusion, he does the exact opposite. He will explode. So this is what happens here. You'll see more of this later with numerical diffusion, as we call it. Okay, one last thing that we will look upon today is this criteria that we found here. R should be smaller or equal 1/2. That can be very strict it's not a nice criteria. It means you will have very, very small time steps. Of course, depending on the viscosity of the Reynolds number in your problem. But here you risk using very, very small time steps. As you can see here, just for this simple problem with startup of a cuvette flow, using you have to use very, very small delta T to be able to have a stable simulation. So what can we do to help this? You have something called implicit methods or implicit schemes. So now we are talking backward time central space scheme. So instead of a first order forward time, we use backward time. And the scheme should look something like this. N plus 1 minus UJN over delta T equals, and then on the other side, the same recipe, viscosity Uj plus 1 minus 2 times center point, Uj minus 1 over delta x squared. But now the right hand side is taken from the new level, n plus 1, n plus 1, n plus 1. So here we can't really use this max-mean method for instability analysis, but trust me when I now say that this scheme is unconditionally stable. You can do whatever you want with delta T, it will still be stable. So backward Euler Euler schemes, they are unconditionally stable in general. So people like them a lot. So you can do whatever you want and it will still be a stable solution. But let's now check this one out here. I have a choice here somewhere. Diff. Then we had choice number 2. And my alpha is 0. So now it's fully implicit. So the stability criteria now is actually not entirely unconditional. Well, if you have fully implicit, it will be. So here you see you will get something negative, which definitely is smaller than 1/2. So if we now run this one, I have to run it like this. Yes, it is indeed stable, no problem. So now, according to the commercial, we can use as big a time step as we would like. So let's check if this is possible. Delta T we had up here somewhere. So now let's use a very big delta T and see what happens. You see, even a bigger delta T, you will have more and more stable, actually. Very strange indeed, but that's actually the case. So now let's see what happens. That's the first time step. So you really jump very far ahead in time. And yes, it looks so stupid, but you have a very big adder. You have a very big adder. Next step, yeah, closing in quite fast into the steady state solution. But you don't really get the time development correctly. It's unconditionally stable, yes, you could use a very big delta T, but the adder is going to be big. So if you find an implicit method, okay, you could use it, but use it with care. I can show you here. If we now use, let's say we have alpha equals 1/2 somewhere here. You can create a hybrid scheme. You take 50% each. So now it's a mix. It's still stable. So, but now 50% implicit and 50% explicit scheme. So if you now look at the solution, it looks rather crazy. So implicit schemes, I won't really recommend it. Also, you see when you want to find a solution here, you actually have to solve an equation system. You have a lot of unknowns. This is unknown, this one, and this one. Well, this we have already. So you need to solve an equation system for every time step. In one-dimensional here, it's not a big deal. But for a full 3D case, this can be expensive with respect to the CPU. So implicit schemes, I would say use with care. If you are only seeking the steady state solution, then it's actually quite okay. And then what people frequently do is the following. Let's say we have alpha here, back to 0, and then I use a time step that is, say, very big indeed. Yeah, we can take him to be 10, why not? Then you can jump to the steady state solution in one single time step. So that can be very convenient. You don't get the time development. That's unfortunate, of course, if you're very interested in the dynamics in the flow, how he develops in time. Then you have to resolve everything in time. But if you're only looking for the steady state solution, then you can jump directly to the steady state with one very, very big delta T. That's possible. Then I would say, why bother? If you are seeking the steady state solution, well, why don't you do it like this? Just forget about this one. Then you have a steady state equation. Of course, you're not interested in the time development. Then don't use time at all, of course. So that would be much easier, in my opinion. So the reason here then, stable, not reading right, but it's still only first order accurate, which then means you choose a big delta T, you get a big adder. That is unavoidable. It's only first order accurate in time. So big delta T means big adder. That's you can't really help it. So no, I don't actually recommend implicit schemes at all. Okay, they are stable. You could use bigger delta T's, getting faster solutions, but the adder is going to be very bad. So use it with care. Okay, that was today's topic. Any questions to diffusion equation implicit gives. That's okay. Next time we will have a peek into the advection diffusion equation and also start looking into exercise number 2. Okay, then we stop a little early today.